All right, everybody, we're going to talk a little bit about resistive forces. So the basic definition of a resistive force, you got FR as your symbol. It's just some force that is slowing something down. Sometimes it can be a fluid that is liquid form. Water can have a resistive force. Ballistic gel, when you're talking about ballistic bullet studies, can have a resistive force. But usually what we're talking about is air resistance. So most of the problems you're going to see on the test are involving air resistance. There's a basic form where the force is always proportional to some constant. Sometimes it's a B, sometimes it's a K. It is just a constant that describes how resistive the force is, and it basically just means that the thicker the material, so air has a lower constant than water, for example, because water's thicker. What makes resistive forces different than other forces is that they're proportional to the velocity, or the velocity squared, rather than to the acceleration like Newton's second law would typically deal with. There's also typically a negative sign because resistive forces oppose the direction. And so the basic thing that's going on is the faster you go, the resistive force gets bigger. So this constant of proportionality, again, that depends on the material you're talking about. These equations always have a similar form, but the basic pattern is that the faster you go, the more the force pushes back, and so eventually it's going to cancel out your acceleration due to gravity or whatever driving force there is, and you're going to reach some type of terminal velocity. The negative sign just indicates that the force is opposing the motion. Okay, so the typical strategy for problems like this go like so. You're going to start with what you know, which is almost always a force diagram. So we'll start with a very simple example of a falling object. At the beginning, when an object first starts to fall, you've got gravity and you've got some resistive force. Let's do the minus kV, and notice it's smaller than gravity. Well, eventually those two are going to be the same size, and that's where you have reached terminal velocity. We call that dynamic equilibrium. So this part is basically a review. And from your force diagram, it's very straightforward to write down the net force equation. So it's winner minus loser equals ma. So it's gravity minus kV equals ma. And then the problems from that point on will diverge and ask you for a bunch of different things. Typically, they're asking you to find the acceleration, the velocity as a function of time, the position as a function of time, terminal velocity, or some other thing. Okay? So this is kind of your starting point. You go from the force diagram, which is always helpful. Sometimes it's even required in the problem, straight to Newton's second law with the net force equation. And from here, that's where the math becomes a little trickier. So I'm going to pause it here for a second. I actually didn't pause. So let's just say that the problem then asked you to find terminal velocity. You've got your Newton's second law equation. Terminal velocity occurs where the net force is zero because gravity and the resistive force have basically canceled each other out. They are equal, and this whole term goes away. In other words, A is zero. There is no more acceleration. So if you are looking for terminal velocity, this becomes zero, okay? And then what you just have to do is solve this equation for V. That becomes pretty straightforward. You add the kV over, so mg equals kV. Vt is the typical symbol for terminal velocity, and it's just equal to mass times the acceleration of gravity divided by some proportionality constant k. That is about as simple as an example problem that I can show you for resistive force. But again, I'm going to go back to review this. We're starting very simple with resistive forces here. Resistive forces always oppose the direction of motion. They are always proportional to the velocity, or sometimes to the square of the velocity. And there is always some proportionality constant. Typically, it's going to be a k. The reason I put this b here is because one of the problems that I've seen on the AP exams has a b instead of a k. But these problems are all of a similar format. They want you to start with the force diagram, get to Newton's second law equation, and then solve for something. I just showed you how to find terminal velocity. In the next video, I'm going to show you how to find these three kinematic functions as functions of time. So we're going to get into how to find the acceleration as a function of time, velocity as a function of time, and position as a function of time, all of which require calculus.